Okay, where we're going. So, Andres received a master's degree from Universidad of Vale in 2016 and a PhD from University of Bristol under the supervision of Paul Skrzypczak, I think, in 2022. Currently, he's a program-specific assistant professor at the UCAL Institute for Theoretical Physics, and his research interests include quantum information theory, quantum resource theories, and expected utility theory. Let us all open our speaker.
Excellent. Yeah, thank you, Leandro, for the introduction, and more generally, yeah, for the invitation. Yeah, I'm very happy to be talking about these things. So, yeah, in today's talk, I'll be going through some connections between utility theories and information theory. This talk is based on this paper that we recently uploaded to the archive, which is a joint work in collaboration with Paul Skrzypczak. And yes, well, okay, so let's see if it's working. Okay, perfect. Right, so this is, okay, I'm calling this kind of like a general landscape. It's somehow like a sketch of the things that we will be going through. So, okay, so we have quantum theory. We can think about quantum theory as a probabilistic theory, and we have information theory, which deals with all of these information theoretic quantities, which depend on probability distributions. So, okay, we can think about it as being also a subset, let's say, of probability theory. And of course, we have quantum information theory here being the overlap between these two. And okay, so that is that. And then the main message I would like to drive home today is that there is a third theory, which comes from the economic sciences, which is expected utility theory, and which, okay, we believe that well, we have found that it is useful like for problems within quantum information theory. And okay, well, this is somehow kind of like the road I have taken, but today, okay, I'm gonna talk about some things lying at the intersection of these three areas of knowledge. All right, so taking into account that, okay, for us people within either quantum or information theory, well, these ideas from economics, they're perhaps the ones that are a little bit exotic. So I'm gonna start going through these ideas first. So, okay, so this is the outline. I'll be going through some of the fundamentals of utility theory. In particularly, well, we will see that the concept that we need from this framework is called the certainty equivalent. I will get to that in a bit. Then I will be kind of introducing some operational tasks in the form of quantum betting tasks. And then we will address how to characterize those tasks in terms of information theoretic quantities. And then, okay, we will explore like these tasks from the point of view of double-sided information, and then, okay, some conclusions and some perspectives. All right. So, okay, so we have expected utility theory. So the first thing to say is that, okay, well, this is a theory from the economic sciences. So economists and people doing finance and these things, this is kind of like the framework that they use to model things. So, okay, and the first thing is that, well, this whole framework was first formalized by von Neumann and Morgenstern in the 40s. And okay, well, I will be going through some of the ingredients. So here we're going to talk about the utility theory of wealth. So just to, okay, so there could be other utility theories of different quantities. It could be any type of goods or assets, but okay, for the purposes of this talk, thinking about wealth, it will be sufficient. And well, arguably that's, at least for economists, that's the most important utility. But okay, so in principle, okay, wealth is going to be simply a non-negative number, right? And well, we can think about it as having units of, okay, any type of currency. And then, okay, the idea of the utility function. So it's basically a function that takes okay, non-negative numbers into the reals. And basically, so in this case, it will be taking wealth. And basically, the idea is that the utility function will tell us the level of satisfaction that a rational agent experiences when acquiring an amount of wealth W. Okay, so so in this sense, we can say that it is like a function that is attached to an agent. Okay, so that is that, and then well, since well, they have two properties that are natural to ask, which is well, it is strictly increasing, and why is that? Well, because it is natural that well, okay, more wealth in principle should imply more satisfaction, and well, similarly, people consider it to be twice differentiable because okay, smooth changes. Okay, one can think that it should imply smooth changes in wealth should imply smooth changes on the level of satisfaction. And then, okay, but then now, okay, we're just gonna be importing some concepts from probability theory. Okay, probability distribution. We're gonna write it like this, right? And then, okay, what economists they call a lottery is basically a pair of okay something that I'm gonna call okay something okay the probability distribution and something that okay we can call a wealth distribution, which is okay basically just a collection of non-negative numbers. So that is that. And then, well, of course, with these concepts, we can now talk about expected wealth. So which is just going to be, okay, the expected value of the wealth distribution. And then, well, okay, sometimes people represent lotteries in this way. So, okay, so here we have the probability distribution, right? And here the wealth distribution. So here is basically, this table here is just telling us, okay, there is a referee and the referee is tossing a coin. And if it's heads, the referee, oops, sorry, the referee is gonna give the player 1 million yen, let's say. And if it's tails, so the referee is gonna give the player 0 yen. And then, well, that's it. That's the lottery. And then, well, of course, the expected wealth is just half of that, right? Okay, so that is that. So far, okay, well, everything seems pretty standard. But now, okay, we're getting into okay more into the details of utility theory. So now we can also calculate expected utility, which is the expected value of the utility on the wealth distribution, which is naturally just the average of this quantity, right? And then, okay, so now this is perhaps the concept that we're gonna need the most in this talk, which is that of the certainty equivalent. So, okay, so I'm gonna walk you through the definition, and then, okay, we're gonna try to explain a little bit what is the meaning of this. So, okay, so this is the definition. So the certainty equivalent is a amount of wealth, which we're gonna denote like this, WCE, certainty equivalent. So it is a amount of, so it will be for a given lottery. So it's like fixed lottery and a fixed agent, right? So U is fixed and the lottery PW is fixed. So if we fix those things, it is the amount of wealth such that if the player receives that amount of wealth, his level of satisfaction will be exactly equal to the expected utility of the lottery, right? So in a way, we can think about this as like the player having like two options. The first option being the lottery, so playing the lottery, or the other option having access to this certain amount of wealth, right? So what this is telling us is that if the player is offered, let's say the referee offers the player this exact amount, the player in a way cannot, he will be indifferent to either choosing the deterministic amount of wealth or the lottery, okay? So that is why, well, it is, people use the word certainty, okay? So, okay, so there is a definition. And then of course, having this, we can just take the inverse of this to have a explicit expression of the certainty equivalent, which will be this, right? Just taking the inverse. And this from here is just to remember that this quantity depends on U and the lottery in question, which is the probability distribution and the wealth distribution. Okay, so that is that. That is the certainty equivalent. And now, okay, well, there are people in economics, they use, okay, a bunch of different types of utility functions depending on what they want to model. In this talk, I will be using, okay, this function, which they call isoelastic utility function. Okay, there are some reasons why this function, okay, is useful for some regimes, but here, okay, we'll be using it because in a way, yeah, in a way, it will be the simplest and non-trivial case, which contains this kind of different types of behavior. So, okay, well, basically, okay, some of the things that economists, they have pushed forward, or they have kind of found out, is that somehow the risk profiles of rational agents, they are encoded in the curvature of the utility function. So, okay, so these are here. This is just a parameter that is going to be telling us a little bit about the behavior of the agent. Okay, so yeah, for the time being, we can just think about it just being a parameter that tells us if the player is either risk averse or risk seeking, or if it's risk neutral. Okay, so if now with this specific utility function, we now calculate this certainty equivalent, right? If we replace this here, so then we can calculate, so this will be the certainty equivalent of the isoelastic function, and we're gonna call that the isoelastic certainty equivalent, and then, well, this is gonna be easier to remember, it's just gonna be the ice. So what is that? Well, okay, as I said, I'm just gonna replace this here. The utility function now is gonna be this specific choice. And if we do that, well, okay, it's not difficult to do that. If we just replace that there, okay, we get this expression. And yeah, okay, well, this is kind of what we're gonna use in a few slides. Okay, so those are in a way the ingredients that we need from expected utility theorem. And now, okay, now we're gonna try to implement them on some operational tasks. So, okay, so here we have quantum state betting. Right, so in a way, okay, one can think about it as, okay, we were inspired by, okay, a quantum state discrimination, which I'm pretty sure that, okay, most of you, okay, are very familiar with this, and also with another task that people in information theory call, okay, horse betting games, which we're introducing, okay, in the 50s, and recently, well, these people from Switzerland, they started to work on this again. And then, okay, inspiring these two things, we can now propose this task, which we are calling quantum state betting. So, okay, I'm gonna walk you through the steps of the task. So, okay, so we can think about this as having two agents. So there's gonna be a referee and one player. Okay, so we can think, okay, the referee, we're gonna think, let's say Alice is gonna be in possession of an ensemble of states, right, of quantum states. So this is just some quantum states, and this is a probability distribution, right? And there are gonna be k of those. Then we're gonna think that Alice is gonna send one of these states to Bob, which we're gonna refer to as the gambler. Let's say she sends row X. So now the goal of the task is for Bob to guess which state was sent, right? Or equivalently to identify the index X. So, okay, okay, so far you're probably thinking, well, this is pretty much standard quantum state discrimination, and that is true. So far, it is in principle the same description as quantum state discrimination, but now, okay, here comes the different ingredient. So now we're gonna allow Bob, so in standard quantum state discrimination, Bob has to output one guess, right? Which is gonna be an index. But now we're gonna allow something a bit more general, which is we're gonna allow Bob to implement bets. So basically a bet is basically a conditional probability distribution, which we're gonna call B, which basically, instead of like choosing one specific index, we allow Bob to, let's say, to bet on, let's say it's gonna be, okay, no, I think I'm gonna put, let's say, 10% on the first index, 20% in the second one, 5%, and so on. So it's going to be kind of distributing, okay, let's say some wealth on each available option, okay, for a specific initial wealth. And okay, so that is that. And G here is considered, we can think about it as being side information that that Bob is gonna extract from from measuring the state that he receives, right? Alice is sending a state, so okay, he's gonna try to extract some information of the state, and that by a measurement, and that information is gonna be G, okay? And then of course, if we do that, well, by Bond rule, we know that well, the probability of obtaining outcome G given state X is gonna be this. So okay, so Bob places that bet. And then, well, okay, we're gonna think now that, well, okay, Alice, okay, if Bob, okay, so after the betting takes place, okay, the real result kind of Alice, okay, tells what the real index was, and according to that, well, she's gonna reward Bob a certain amount, which is gonna be given by this function OX. So this OX is basically, okay, if index X1 was the one that she sent, so she's going to reward Bob an amount of wealth, which is given by OX1 and whatever proportion Bob allocated to that specific index. Okay, so yeah, okay, so this function is proposed by Alice, and okay, it is known for yeah, but Bob has access to, okay, Bob knows what this function is like from the very beginning. So, okay, so from here, okay, just to emphasize, the amount of wealth that Bob receives after one round of the game is given by this, right? The proportion that he bet on the specific index and OX, right? All right, so here then we can see that we can have then a kind of, this is pretty much like a lottery, because, okay, we have a distribution of wealth, and we also have a probability distribution, but now, okay, we're thinking about it with two variables, right, with X and G. So given that, so now we can, again, it is a lottery, so I can calculate the certainty equivalent. So in other words, how, okay, you know, yeah, we can also think about the certainty equivalent as how attractive the Bob finds the lottery in question. Or also, okay, the amount of wealth that Bob is willing to accept from Alice and not playing the game. Okay, so if we calculate that, okay, sorry, if we spell out that for this quantum betting task, so okay, so we have, this is just the definition from the certainty equivalent, right? Just the inverse of the expected utility, and then, well, of course, we have two random variables, right? And then, well, this is what we were just constructing, right? This is wealth, right? Odds times the bet. And then this part, well, this is just the joint probability B, G, and X. And then, well, of course, yeah, I'm just having here with colors, well, the dependence, right? In red are kind of like the objects that Alice is in control of. And in green, the objects that Bob can kind of manipulate a little bit. He can choose measurements and he can propose a betting strategy. Okay, so that is that. That is the certainty equivalent for our quantum betting task. And okay, well, this is a remark that now Bob, in a way, can control a little bit this P of X and G, and similarly the wealth, right? He can have some influence on the amount of wealth that he is gonna potentially is gonna receive. And okay, so this is the certainty equivalent. And then, well, okay, one can imagine that we would like to kind of maximize, well, okay, the player or the gambler, Bob, is in his interest to maximize this quantity. Well, in this case, it will be kind of like an ideal scenario, right? It will be if he's given the option to choose between something deterministic and the stochastic process, well, he would like to know, okay, how much value he can assign to the stochastic process. So, okay, and that will be this quantity. Okay, so this is the quantity that we want to kind of explore. And okay, and just to kind of to come back down to earth a little bit, so we can see that these type of tasks, they generalize quantum state discrimination, because we can do the following. We can think about, okay, I'm going to think that the rational agent is going to be a risk neutral. In this sense, it means that, okay, the risk parameter is 0. And we're going to imagine that Alice, the referee, is offering constant odds, meaning that this function OX is just a positive, just a positive number. And if we do that and we analyze this function that well, we had in the previous slide. So, okay, I put R equal to 0. So basically this part disappears, this part disappears. And then, okay, that is that. And then, well, I just get this, right? And then, well, I'm pretty sure that most of you will recognize this quantity. This is pretty much the probability of success for a quantum state discrimination task in which Bob is implementing measurement M, and the referee Sen is using an ensemble of states E. So, sorry. So, yeah, okay. So this kind of interlude here, or this slide, is just to kind of, okay, we have these quantum betting tasks, and we can think about them as being kind of a generalization of quantum state discrimination, right? Because, okay, here I specified these two things, but in principle, I can explore this quantity with R being any real number and this OX being other functions other than the constant function. Okay, so this is that. And then, okay, so here we have a first result. All right, so now we're gonna think, okay, a quantum state betting game with this ensemble of state, just an arbitrary one. We're gonna keep thinking about constant odds, and Bob, okay, is gonna use a fixed measurement M, and if we do that, then okay, one can think that we would like to analyze a ratio like this. So here, what is the meaning of this ratio? So okay, here we're comparing two eyes, right? So okay, this one from here. So okay, the first thing is that the first thing to notice is that we have the same game. So we are kind of comparing two scenarios that have the same game. Alice is offering the same rewards, and she's using the same ensemble of states. But then now the player here in these two scenarios, the player is gonna behave differently. So in here we have a fixed measurement M, and then, well, Bob is allowed to maximize over all possible betting strategies. But in this case, now we're gonna restrict Bob that he's also gonna be allowed to maximize over all betting strategies, but the restriction now is gonna be that he's only gonna be allowed to use a class of measurements that is called people call it uninformative measurements. Basically, they are like measurements that they have POVM effects being proportional to the identity. That is kind of like the subclass. So we can think that here basically we are comparing somehow we're comparing the advantage that M has over this class, right? We can think about it in that way. So what is the advantage that M has against all measurements in this class? So if we do this, and then, well, this is one of the results that we derive. Well, not in this paper, but in our previous paper, it is that this quantity is exactly equal to an information theoretic quantity that people call Arimoto's mutual information. So so this is it. So basically, so let me. Well, the first thing to say is that this was introduced by Arimoto in the 70s. And well, this is perhaps so the first thing to say is that, well, so far, I haven't mentioned anything about information theoretic quantities. So just to say that we constructed these games, this quantum state betting, and we in a way, this kind of operational in the sense that we're comparing two different scenarios, and we want to see, what is the advantage that this player has over this other player? And then, well, this is operational in nature. So left-hand side is operational, and right-hand side, well, it is explicitly a information theoretic quantity. So that is good. And also the other nice thing about this is that, well, here we don't need to specify any ensemble. This works for any ensemble of states. And also I don't need to specify M. It can be any fixed measurement. And okay, well, here this should be R. And in principle, this R here, well, it could be any real number. So okay, so that is good. And then, okay, well, this is precisely what I was telling at the beginning, that somehow, okay, this type of result, it lies at the intersection between, of course, well, we have quantum. This is a quantum betting task that involves a ensemble of states and so on. And well, also we need ingredients from expected utility. We need this concept of the certainty equivalent, and well, the right hand side is information theoretic in nature. So okay, so this was okay. We had that, and then but also okay, we can do a bit more. So okay, this is the same. The same line that we have before. But then, well, it turns out that one can also write it in this way. One can write it as a difference between something that, okay, people call conditional Rényi divergences, and this one here, which is the standard Rényi divergence of order 1 over R. So, okay, these conditional Rényi divergences, yeah, we can just think about them as being kind of like a Rényi divergence, but then kind of like with this conditional here, right? Okay, well, this conditional Rényi divergence is the one that was first proposed by Bleuler, Lapidotham, Pfister, which, okay, that's why I'm using the BLP here. And okay, and one thing that, okay, people have proven about this quantity is that, well, okay, it satisfies a kind of data processing inequality, which guarantees that this difference here is always greater or equal than 0. So, okay, so this in a way, well, okay, this is then telling us that, well, okay, there is an advantage here when using M against this class of measurements. Okay, so that is that. Okay, so far, okay, we just kind of manipulated the result just to see it from another angle. Okay, so then is, okay, what are we doing this? So, okay, okay, before that, we can also see that, okay, if we have this difference, sorry, yeah, no, we can have this type of difference because, okay, we can prove something like this, that this part from here is, well, is actually, yeah, well, this is equal to this BLP conditional Rényi divergence, the part in which the the player has access to side information, right? And then here, well, it will be the case without side information. Also, in terms of the notation, yeah, sorry, here, okay, this is B of X and G, which is the same. And here, from now on, I'm gonna OX, well, it will be kind of the same. And I'm combining M and E, because M is, okay, the measurement, so it's kind of G, has G, the random variable, and this one has the random variable X. So yeah, I'm combining these two into this kind of this notation, right? P of X and G. So okay, that's the notation that I'm gonna use from now on. Oh, and I think, sorry, I have a typo here. There should not be a Y here. Oh, this one is just OX and OX. Do I have it? Yeah, just like this. Sorry, yeah, it is a typo. There is no side information on the odds. So yeah, apologies for this. Yeah, just like this. So okay, so that is that. So okay, so we have these two kind of sub results, let's say. So okay, why it is useful to see this in this way? Because okay, so now it's like we can ask the following. So okay, we have seen that of course this equation 11 here, there is no side information at all. So the player does not have inside information, and the okay, kind of the entity in charge of proposing the odds, well, they don't have any side information. But well, here the player, where we allow the player to have access to some side information, but then the let's say the referee does not have access to any side information here, right? So the the motivation then was like, oh, okay, well, we want to see what happens when okay, if we allow the entity kind of in charge of proposing the odds to have some sort of side information from the stochastic process, which is X. So then kind of we have like a few scenarios. So of course, when it comes to the player, we can think about the player either having access to side information or not having access to side information, and the same for the referee, right? Having access or not having access. And then, well, depending on what out of the 4 combinations we have, so okay, we're gonna think about the stochastic process just being any of these kind of probability distributions, right? Which is, so yeah, just to remember G, okay, we're gonna think about G as the side information kind of that can be available to the player, and Y, the one that can be available to the referee. So, and here, well, this distribution is just telling us, okay, how correlated they are. Okay, so if we do that, so of course, here we have like 4 combinations, right? So the first one is basically, okay, no site information at all. Okay, we have this. That's what we saw from the previous slide. And then if we consider site information available to the player, so now we, okay, from the previous slide, we have that, okay, this is kind of characterized by this PLP conditional Rényi divergence. But then now if we ask about if we think about allowing the referee to have access to site information, so then we have these 2 other possibilities, right? A scenario in which only the referee has access to site information, and then, well, okay, in a way, the most general case in which we allow both to have access, right? So then, in a way, let's say from the physical point of view, this was kind of like the motivation, like from an operational point of view, we wanted to explore, okay, what happens with these scenarios. And then, well, of course, the question is like, and the intuition is that, well, okay, if these 2, okay, it is possible to characterize these 2 in terms of information-theoretic quantities. So, okay, well, hopefully these quantities that appear here, they are at least information-theoretic in nature. So that is the question, like if we can somehow think about the quantities that we get here after this optimization is performed, if we can think about them as some form of measures. And okay, well, what okay, what we want to propose is that well, yes, it seems that that is the case. And then, okay, given that, okay, well, just to say that, well, these optimizations, similarly to these ones, one can explicitly perform them in the sense that we can have a explicit expression of what this quantity is. And okay, well, it is a bit long, but okay, it is there in the paper. And so, okay, so we have these quantities, and then, so, okay, in particular, well, okay, one would like to check some of their properties, right? And okay, so then here we have, yeah, I'm gonna be telling you a little bit about 2 of their properties. So the first one, okay, so is this, which again is motivated by kind of like those operational ratios that we are kind of comparing. So similarly, okay, so here we're gonna, we can be interested in comparing this ratio. So again, in this case, we can think about this as kind of comparing 2 game scenarios. So this one here is basically no site information, right? We don't have any additional random variable. And this one here, we're going to be using the new one, the new scenario in which the entity proposing the odds has now access to site information. So we want to, okay, what happens with these 2 cases? And then, well, of course, if we just replace kind of these quantities that we already have here, so of course, well, we do get something like this. But then the question is, okay, the question we have is like, okay, well, what is happening here? And then, okay, well, the first kind of result, which in a way, when we can think, I guess, one can think about this as some form of data processing inequality for this quantity. So, okay, this is kind of one of the things that we prove. And well, okay, and then, okay, well, the first thing to say is that, well, at the beginning, this looked a bit kind of unintuitive in the sense that, I mean, because if we put these things into words here, this scenario is basically the case with no side information, whilst this one is the case where in which the referee has access to side information. And then somehow, if we can, but then again, this i's is a quantity that pertains to the player. So somehow, well, in words, this is telling us that somehow the player is benefiting from the referee having access to side information. So at the beginning, okay, yeah, well, we found this a bit unintuitive, but then, okay, one way to come to terms with this is that, yes, well, even though in comparing these two game scenarios, even though it is the referee that has access to side information, yeah, okay, I think the caveat was that we should not forget that the referee, of course, being in possession of the odds, he has to make the odds public, because, well, okay, that's the setup of the game. Like, and then Bob, the player needs to be aware of what he's potentially gonna be rewarded, like before the game starts. So in a way, kind of, yeah, there is kind of, yeah, we can think about it as like, yeah, the referee has access to side information, but then at some point he has to make public the odds, which in turn depend on the side information. So in that sense, it's like, okay, well, there is some amount of side information kind of like on the system. So, okay, well, and then, okay, well, that in a way, okay, makes this perhaps not that unintuitive. So, okay, so in words, this is kind of the conclusion from this part, is that, okay, the referee having access to that information, it still benefits the player in this way, in the sense that, okay, there is still kind of like an advantage here. All right, so, okay, but then, okay, this is one of the cases, but then the other natural case is this one, in which we're gonna be comparing cases again with side information, but now if we look closely here, this will be kind of one of the vanilla cases in which the player is the one having access to side information, right? And the referee is just the standard referee. And we compare this scenario against a scenario in which now the player, okay, does not have access, whilst well, the referee is the one having access to side information. So of course, we're replacing these things from here, right? Okay, well, we get this difference, but then, okay, we have that difference, and again, we want to see if we can make a statement about these things, and then what this one of the another result that we have in the document is that, well, this quantity is indeed greater or equal than 0. Sorry, I didn't write down here. These are, we can think of, yeah, I think for it, we can think about it as being, yeah, positive, yeah, like any non-negative number. Yeah, I don't have this in the slide, but right. So, okay, but then we found out that this is always greater or equal than 0. And then, okay, well, this one, it is perhaps a bit more natural, because in words, again, this is telling us, so, okay, so we're comparing two scenarios in which there is side information kind of like in the system. And then in a way, this is kind of now, okay, this is a bit more intuitive, because in a way, this quantity, which represents this, is that the player having, let's say, direct access to the side information, right? He's receiving Y. Unlike this case in which yeah, there is some side information in the system, but it is the referee who first kind of acquire it. So of course, well, if we do compare these two cases, so okay, it is natural that the case having direct access to side information, it will be better than having an indirect access to it. So, okay, so that's kind of in words, that is kind of like the meaning of this inequality. Okay, which is, okay, well, more intuitive. So let me see. Okay, it's pretty much about time. So yeah, so in a way, this is kind of like the summary. So in a way, the starting point was these first two, the vanilla case, no side information, and well, the other case, which, okay, was already known in the literature, which is the case in which the player has access to side information, and then we play around kind of like considering these two scenarios. And then we kind of, we're making the case that these quantities should be interpreted similarly to this one, some form of conditional Rényi divergences. And then what we kind of, I mentioned here only kind of like those two inequalities, but in the paper, we explore a little bit some other properties. So for instance, being non-negative, and also, sometimes people expect from conditional Rényi divergences to reduce to the standard Rényi divergence. So in the paper, we kind of check these things. So, so the message, let's say, from this part is that, we can characterize these quantities, and the object that we get here, we believe that it should be interpreted as a conditional Rényi divergence. Sorry. And then, as I was saying, we can have somehow like a hierarchy between these quantities, something like this, in which, we can reduce from one to the other according to these levels of independence or dependence, right? So that was one of the kind of some of the results that I wanted to talk about. And so, those are kind of what I just said, the conclusions that basically, we're talking about operational tasks based on betting, these ideas from expected utility theory from the economic sciences. And now we are adding this kind of extra kind of double side information and playing around with that. And then, the fact that, it seems that this way of thinking, it seems like, we have these other quantities emerging here, like these conditional Rényi divergences that they, in a way, characterize these tasks. So some other things that, just to briefly mention this, that we also explore in the paper, but unfortunately, I don't have time to properly address here, is that, we're in, in the talk, I'm basically talking about expected utility theory. But there is a where economists, they have come up with a generalization of expected utility, which they call prospect theory, and we play around a little bit with this generalization and exploring these tasks now from this more general point of view. And it seems that even though this theory is a bit more general, we can still kind of quantify kind of these tasks even here. And there are other quantities that appear there, but I'm not gonna get into that. And also, I meant in this talk, we kind of went through a utility theory of wealth. So wealth was kind of like the quantity of interest, but we can play around with that and introduce other other kind of quantities of interest, and in particular, we can talk about wealth ratios. And over there, it seems that there are even some other quantities now can also be kind of interpreted with these scenarios. And but I'm not gonna get into that. And this part, which some implications to quantum research theories. I briefly mentioned about informative measurements, but it can also be addressed for non-constant channels and things like this. And just like a few words about this, which is kind of so in basically, we're kind of, the way I see it is like, we are kind of trying to see, in this case, information theory, or these results in the overlap between quantum theory and information theory from the point of view of expected utility theory. But in principle, one can also think about using these ideas from economics now to other areas in physics. So for instance, one can think about stochastic thermodynamics, in which there are also, we can think about stochastic thermodynamics also as being a subset of probability theory. They use probability distributions to model kind of like these these processes. So, and we found out that there is also some, it is useful to try to see these things from the point of view of economics. But and also, there are other areas in which we believe we can gain some insight by using these concepts and ideas from economics. And but of course, well, this is kind of like for perspectives. And yeah, as I said, like the full details of this can be found here. And yeah, well, no, with that, I would like to thank you for your time.
Okay, thank you very much for your nice talk. And now I'll open for questions if the audience has any.
Hi, thank you for your nice talk. I'm just kind of curious. You apply the information to the finance wealth problem, and I'm considering, do you have a real situation that this can be used? Like, do you consider how like the operational like measurement which will be used in this kind of wealth expectation measurement? Do you consider any practical situation?
Right. Yeah. Well, yeah. The first. Okay. Yeah. No. Thank you for the question. When it comes to where is it? Yeah. Even here. Yeah. When it comes to kind of okay, well, things that are kind of okay, practical applications of these things and so on. Yeah. The first thing is that, for instance, this this concept of certainty equivalent, in a way, I mean, we are not kind of proposing these quantities from the scratch. In a way, the way I see it, we are kind of importing these kind of ideas like from economics, because okay, people over there, they have used these quantities for over 50 years. So one thing to, so I'm saying that because uh, yeah, in a way, kind of like for economists, this is kind of like their bread and butter. In a way, like they use this formalism like on a daily basis. And in particular, this kind of this certainty equivalent, well, that is a quantity that they can measure, in the sense that, okay, well, the type of experiments that economists they do is that, I mean, because these quantities, they emerge in decision problems, right? So in a way, we need an agent, and we need an agent kind of, and having being presented like different options. So in this case will be lotteries. So it will be like a lotteries, and then the agent decides which lottery he prefers. And well, according to that information, and if they repeat that a bunch of times, and even with different people and so on, they can try to model, okay, well, kind of the risk profiles of agents. So yeah, in a way, okay, when it comes to kind of like practical things, yeah, in a way, yeah, economists, I mean, they have done these type of things for a long time. And yeah, so these kind of quantities, in a way, yeah, it's something that can be kind of measured like from yeah, from this type of kind of decision problem kind of games.
Yeah, thank you. So is this are these tests applicable extended to like a communication case, like two long distance player that can like have the play the game? Is this can be extended to like communication case?
Uh, yeah, no, thank you for that. Yeah, no, that's a very good point, because yeah, right now, yeah, no, exactly. Right now, here, yeah, well, even here in this setup, yeah, there is, yeah, exactly. Yeah, as you're referring to, there is one referee and one player. So in a way, there is, everything is kind of local in that way. We're not talking about kind of distances or like communicating anything. But yeah, I do. Yeah, just to kind of answer your question shortly, I do think that yeah, these things can be kind of, or at least, okay, perhaps not the exactly this setup or this task, or the ideas kind of like behind it, this idea of utility and risk and certainty equivalent and so on. I do feel, and okay, with okay, I'm still collaborating with Paul, and we do think that that is the case. So that's why I mentioned here at the end this thing on coding theory, because yeah, we do believe that yeah, there should be a way kind of like to because well, of course, I mean something that that is common, is a common factor between these things I mentioned here is that okay, they all deal with stochastic type of things, and but also they also deal with kind of information theoretic quantities, right? So yeah, no, yeah, that's a good intuition, and I mean right now, okay, we don't have anything concrete, but I do believe that that is the case.
Okay. Oh, thank you. Okay, nice. Thanks.
Do you have any more questions? I think we don't have here, but I do have, I think, two questions. One is that kind of the beginning, you define an isoelastic function. I don't really remember the name. And you have three different scenarios according to the parameter R, right? So you can be like risk averse, risk seeking, and risk neutral. And when you start showing your results, if I recall correctly, you do that for the risk neutral case. Is there any difference if you're on like the risk seeking or risk averse settings? Because from this isoelastic function, it appears that perhaps it's not going to be, but I'm not sure. So
Yeah, yeah, no, thank you for that. Yeah, I did mention the the R being equal to 0 here, and sorry, here. It was basically yeah, okay, kind of like to reduce or to gain a little bit of intuition of what this quantity is. And we see that okay, for R equal to 0, we recover the figure of merit of standard quantum state discrimination. But then yeah, I mean, this is kind of just like a particular case, let's say. But when it comes to the result, yeah, sorry, I didn't explicitly write here. Okay, well, probably yeah, okay, I wrote it like in here, but yeah, with a different symbol. Here it should be R. So in principle, yeah, this kind of, yeah, we don't need to assume any specific range for R. R in principle, yeah, it will be from -infinity to infinity. So yeah, I think, yeah, no, so this stuff, okay, this result in particular, and it holds for any R. But having said that, and okay, here R is general. When it comes to the inequalities, however, I think, well, okay, I didn't write it here. I apologize for that. But this for these inequalities in the paper, we did it for positive R's, so for risk-averse players, and right now, yeah, I'm trying to remember what was the difficulty for negative R's. Yeah, but yeah, no, yeah, okay. Right now, I don't remember exactly why we couldn't kind of say much about risk-seeking players, but okay, for risk-averse players, yeah, we do have these inequalities. But yes, but yeah, in a way, I mean, there's still, I mean, we did, okay, well, we did a few things there, but yeah, I mean, of course, there are still things about here that, okay, we don't fully understand yet, but yeah, no, that is the case. But okay, but then until here, in principle, and then the previous ones, yeah, R is in principle general.
okay, so for these equations that you're showing, R is going to be general, but when you're kind of establishing this data processing inequalities, you just consider for non-negative or positive R?
Yeah, exactly.
Okay. And that leads me to another question, because when you define these equalities on the next slide, you also mentioned briefly a hierarchy that you can have between them. But I was kind of curious because when you establish the data processing inequalities, you establish them based on side information that the referee possesses or the player possesses. So there is some kind of relation between those data processing, like is one let's say, strictly larger than other, or can you say anything about them?
Okay.
The relation between
Because okay, let me see if I'm getting the question right. Because from here, I mean, in a way, the one way to read this is that kind of this N1, it's kind of like in the middle, right? Between between the standard Rényi and the BLP, right? That's one way to read this. This is always greater than this, and N1 is always greater than the standard Rényi, and BLP is greater than than N1. And so in a way, this will in terms of like the hierarchy of the order, this will kind of like explain or specify a specific order between these three. And because, okay, in this diagram, by these arrows, what I mean is that I can reduce, or this quantity becomes equal to this one when this condition is met, right? And this is just saying X is independent of G. So, and actually, well, this is a property that is expected from from these conditional Rényi divergences, that whenever you have the side information being independent from the original random variable, so you expect that the conditional case it just reduces to the to the standard Rényi, just pretty much like in the for anything that people call conditional. So that is the meaning of this diagram. But so in terms of the less or equal kind of order, okay, well, with these two inequalities, we will have kind of like an order for this, right? But then when it comes to, yeah, I think that, that's a good question, because now, yeah, if we can think, okay, what if I want to compare the order between these and these two, for instance? Yeah, I don't think we did that. Yeah, I will expect that perhaps this one should be larger than these two, but no, I don't think we did that. Yes, if I think that perhaps answer your question.
Okay, okay then. I think we don't have any more questions. So let me thank you again for the very nice talk, for agreeing to come in here. And I'm going to stop the recording.